This video deals with basic electronics. Now, there's three basic concepts that you need to know about. First of which is something called voltage. Now, voltage is defined as the energy per unit charge, but it's easiest to think of it as sort of a pressure that's driving the charge through the circuit. There must be a voltage source for any electrical current to flow. The units for voltage make sense, a volt, and when we look at a device in a circuit, we usually say that there is a voltage drop or a voltage difference across the device, and you'll see more about that later. Okay, so the next is current, and this is the rate of flow of electrical charge. The greater the voltage, the greater the current, assuming that this resistance here that we'll talk about in a minute is constant. The units for current is the ampere or the amp, and it's very common to see milliamps, which is 1,000th of an amp, 1 times 10 to the minus 3 amps. Notice that abbreviation there, small m, a for milliamps, or sometimes even microamps, which is 1 times 10 to the negative 6 amps. Okay, so the third one is resistance, and resistance is defined as opposition to the flow of current, and when the voltage is the same, the higher the resistance, the lower the current, which makes sense because resistance is opposition to current. Then when the opposition gets higher, then the current's going to get lower. The units for resistance is the ohm. Almost always you'll see this Greek symbol here for the ohm, and you'll often see kiloohms, which is 1 times 10 to the plus 3 ohms. A very important formula when dealing with any kind of electrical circuits or electronics is Ohm's law. And Ohm's law defines the relationship between the three quantities that we just spoke about, voltage, current, and resistance. So here is the basic formula. V is equal to R times I. And we'll go through a couple of real simple problems here. Okay, so the first one is, suppose you have a 1 kiloohm resistor and you've got a current of 15 milliamps flowing through it. We want to know what is the voltage across the resistor. Okay, so we're going to use this formula, V equals Ri. Notice that we've got to use the appropriate scientific notation for kiloohms and milliamps. So 1 kiloohm is 1 times 10 to the plus 3 ohms. 15 milliamps is 15 times 10 to the negative 3 amps. When you multiply this out, 10 to the third times 10 to the minus 3 ends up being 10 to the 0 power, which is 1. And so we basically get 15 times 1, which is 15, and so the answer is 15 volts. Okay, now, you're going to need to be able to solve algebraically for these other variables here, R and I. So here is the first one. When you solve for I, you have I is equal to V over R, just basic algebra there. All right, a problem where involving this formula equation, we have a 5 kiloohm resistor, and we have a voltage of 10 volts across it. What is the current flowing through the resistor? Notice how you have voltage across the resistor, but you have current flowing through the resistor. Okay, so we want to solve for I. I is equal to V over R. So we have 10 volts divided by 5 times 10 to the third ohms. We divide this out. That gives us 10 divided by 5 is 2. 1 over 10 to the plus 3 is 10 to the minus 3. So we have 2 times 10 to the minus 3 amps, and we saw in the last slide that 10 to the minus 3 amps is milliamps. So the answer is 2 milliamps. So here is the third form of Ohm's law, solved for resistance. R is equal to V divided by I. So we have a certain resistor that's got a voltage of 5 volts across it, while there is 2 milliamps flowing through it. We want to determine the resistance of the resistor. So I'm going to use this form of the equation. So 5 volts divided by 2 milliamps, which is 2 times 10 to the negative 3 amps. 5 divided by 2 is 2.5. 1 over 10 to the minus 3 amps is 10 to the plus 3. So we have 2.5 times 10 to the plus 3 ohms, which is 2.5 kiloohms. So now we're going to talk about some electrical devices that you're going to be using throughout this semester. And by far the most common that you'll be using in every one of your projects is the resistor. And the resistor is a little photo of it down here. They have a fixed resistance value associated with them, and they're almost always used to control current, although they have other uses in circuits. But anyway, these little stripes here is a code, a color code, that will determine the resistance value of each one of these resistors. And we'll talk about that code in the next slide. One thing that's important to know about resistors, there's no positive or negative end. So when you connect them in the circuit, it doesn't matter which way that you connect the ends of the resistor. So here is a chart that can be used to decode what the resistance is of a particular resistor. And this is showing 4 bands, and the first band, the color, indicates the first digit of the resistor value. The second band gives you the second digit of the resistor value. And the third band gives you the multiplier. And the multiplier, easiest way to think of that is the number of zeros that you have to add to the first 2 digits that you got from the first 2 bands. And then the band 4 here is the tolerance. We're not going to be concerned with that so much, but it's basically telling you that if it's a silver band, for example, that means whatever resistor value you came up with, the actual resistor value is within 10% of that particular value. Okay, notice that the colors go black, brown, and then the next few colors are the colors of the spectrum: red, orange, yellow, green, blue, violet, and then gray and white, and colors are associated with the digits. This is just to help you remember the color code, but I'm not going to ask you to memorize this. If I ask you this question on a quiz or an exam, I'll give you the actual code to work with. Okay, so let's try a few examples. So let's say that you picked out a resistor, and the first band was brown, the next one was red, and the third one was orange. Remember, we're not going to be dealing with the tolerance. Okay, so brown. You look on that chart here. Brown is symbol associated, or the digit associated with it is 1. So we have 1. And then the next band is red, and red is associated with the 2, so the next digit is 2. And then orange is associated with the digit 3. Whoops, I'm in the wrong place here. Okay, the digit 3. Okay, so that means that you're going to take this value and you're going to multiply it, this value, the 12, you're going to multiply it by 1,000, which is just adding 3 zeros. So an orange, meaning 3, means you just add 3 zeros to it. So this resistor would have a resistance value of 12,000 ohms, or 12 kilo ohms. Okay, let's try another one. Yellow, black, brown. Okay, yellow, we look on the chart, 4. Black is 0, so the next digit is 0. Brown is 1, so that means we're going to take that value, we're going to add 1 0 to it, and so we end up with 400 ohms. Okay, let's try a couple going the other way. Suppose we had a 330 ohm resistor. What would be the color code? Well, 3 associated with orange. Second digit is also 3, so that's another orange band. And then we have 1 0, which means that the third stripe would be brown. So we have orange, orange, brown. Okay, one more, a 10 kilo ohm. Again, the 1 is brown. Then we have a 0, the 0 is black. Okay, then 10 kilo ohms means 10,000 ohms, so we need now 3 zeros. So we're going to take the multiplier here of 1,000, so that's going to be orange. So we end up with brown, black, orange. Here are two components that we'll be using a lot of during the semester. The push-button switch, which you can see is right over here, and LEDs, or light-emitting diodes, which is shown right here. Okay, so first of all, the switches. Here's kind of a variety of different styles of switches. I think the ones in your kits probably look mostly like that, but they all have 4 terminals, and when we put them on the breadboard, there is a gap in the center of the breadboard, and we typically put 2 of the terminals on one side of the gap and 2 on the other side. Okay, now when you press the button on the switch, what happens is these 2 terminals right here get connected together, as well as the 2 on the other side. And so in that way you can complete a circuit and possibly, if these are connected to an input port, the port can sense the fact that the button is pushed. Okay, now light-emitting diodes. This one is a red one, and I think you have red and green in your kits. All diodes conduct one way. Now, you'll notice here that this particular diode, there is one lead on the diode, this one right here, that's longer than the other one. And that lead gets connected toward the voltage source, and the other side gets connected toward the ground. Now, if they're not connected that way, they just don't work. And so if your light is not lighting up and it's supposed to, that's the first thing to check. Their maximum current is around 20 milliamps. This varies according to the kind of LED it is, but that's the ballpark value. So as a result, they're always used with a resistor to control the current. The resistors that we'll use are the 330 ohm resistors, which are included in your kit. Another device that we'll make a lot of use of in our projects is a potentiometer, and that's shown right here. Notice there are 3 terminals right there, and this diagram over here shows a kind of schematic diagram of how these potentiometers are often wired up. The important point is that as you turn this knob on the top here, what happens is this centered terminal here moves either down or up. And so as a result, what happens is if you're moving it up, it increases the resistance between the center terminal and down here, which is connected to the ground in this diagram. And it decreases the resistance between the center and the top terminal. On the other hand, if you're moving this down, then the resistance between the center terminal and the ground here becomes less, and the resistance between the center terminal and the top terminal becomes greater. Typically, these are often used when this top terminal is connected to 5 volts and the bottom terminal is connected to the ground. Then, as you turn the knob, since the resistance changes, then the voltage also changes between the terminal and the ground. And that's got a lot of applications in projects, as you'll see. 2 more devices that we'll be using quite a bit is a transistor and a photoresistor. Okay, so the transistor, again, is a 3-terminal device, and as we say down here, it acts as an electronic switch. So this center terminal here can be connected to a port on the Arduino, and then with a very small amount of current, that can control a larger current between these 2 terminals here on the outside, the emitter and the collector. Typically where we use these is where we want to control the device that consumes a significant amount of power, electric current, that the port can't provide. An electric motor is a good example of this. Okay, the photoresistor is a device, very simple. Its resistance changes with the light intensity. So, if you have this in the dark, then the resistance between these 2 terminals might be relatively low, and then light shines on here, the resistance increases between the 2 terminals. And of course, this can be very useful in sensing light changing.